All right, folks, let's go over this. So who can tell me their approach, their strategy to this synthesis? Two-step synthesis, two separate reactions, right? So we're forming something that we're going to isolate, right, and then submit to a second reaction.
For the first step, we can use an acid and alcohol to turn this into an ester.
Okay, so one method that we can use is esterification, right? So we could take catalytic acid. Do you have an alcohol in mind, Kevin?
Yeah.
Which one?
Just ethanol.
Ethanol, great. Right, throw in some cheap alcohol. All right, and that gets us to the ester. Where do we go from there?
Then we can have it react with an amine.
Good. Which amine do you want to add?
Didn't do that part yet.
What's that?
Didn't do that part yet.
Okay, so we want to add an amine. What does that amine have to have on it? What are the three, right? Nitrogen makes 3 bonds. What are the 3 groups on that amine?
It's gonna be methyl,
Yep.
hydrogen,
Yep.
and your little
Ester.
Oxygen.
Methoxy group. Right, now alkoxy group, this one's supposed to be methoxy. Right, so this is the amine that we would need to add, right, in order to get to here. So this is one way of approaching this. Right, I would say there's a better one way that's better. Anybody do it differently? We're going to a really important reaction on Friday. If you say that again.
If we did the first part, the base catalyzed.
So we don't want to do base catalyzed, because if we treat this with a base, we're just going to pull a proton, and then we're dead in the water, right? We can't, once we deprotonate a carboxylic acid, not much is going to be able to add to it, because it's so not Yeah.
Do you want to make it into acid core?
Yeah, so why would we want to do that rather than an ester?
That I'm not really sure.
Okay. So if you guys didn't hear Bernadette, she suggested that we turn the acid into, rather than an ester, we turn it into an acid chloride. Right, we would do that using thionyl chloride. Okay, and then we can, for the second step, basically just add the same amine. Right, and we can either add 2 equivalents of that amine, or we can add 1 equivalent of that amine and then some base that we choose, some cheap amine base for the reaction. Okay, both of these reactions work. Both of these syntheses work. I would say the reaction, or the route on top, right, the second one that we talked about, is the better of the 2. Why would that be the better of the 2? Higher yielding. Faster. Yeah.
Because we know that like the Cl group is like the best nucleophile.
Okay, so I would say the chloride is a better leaving group than the alkoxide. So what does that make in terms of this reagent as a whole? Is it a better reagent or reactive reagent? Yes. Yeah. Right, so acid chlorides are going to be much more electrophilic than esters. So we would expect the substitution to be faster, right? Because we're making a much more reactive electrophile. Right, so again, both will work. I would say the route on top is the one we would typically take if we were to go into the lab and make the Weinreb amide, or the amide from the carboxylic acid. All right? Any questions about this? Okay, so this amide that we're making, we're going to see this again in this chapter. This is a very specific type of amide called a Weinreb amide. and what makes the Weinreb amide different from other amides is the substitution around nitrogen, right? So Weinreb amide specifically is going to have a methoxy group and a methyl group on a nitrogen, right? And this substitution pattern around nitrogen gives this amide special properties that other amides don't have, and we'll see that later on in this chapter. Okay. Any questions before we move on from the synthesis? Okay. So we're going to start chapter 10 today. Chapter 10, as I've said before, follows the themes of chapter 8 and chapter 9. Right? So chapter 8, we looked at additions to aldehydes and ketones, right? Additions of oxygen and nitrogen nucleophiles to aldehydes and ketones. Chapter 9, we looked at the addition of oxygen and nitrogen nucleophiles to esters, to amides, acid chlorides, right? So the carboxylic acid derivatives. Here we're going to be looking at different nucleophiles. So we're going to be continuing that theme, right? Additions to carbonyls, but looking at a different set of nucleophiles. Right? The first set is going to be hydride nucleophiles. Right? And then the second set is going to be carbon nucleophiles. Right? Obviously, they're not going to come in this form. We're not going to have an H minus or a C minus. Right? They're going to be attached to things, but that's essentially how we want to think of them. All right? In this chapter, we're going to start talking about the concepts of oxidation and reduction, or oxidation state within organic chemistry. Right? Because we're adding hydrides, we can take something from a higher oxidation state and reduce it down to a lower oxidation state. Right? So it's important that we recognize the different oxidation states in organic chemistry. Now I should say that different people do oxidation states in organic chemistry different ways. We're going to try to take the most simple approach, right? And basically look at the number of atoms, number of electronegative atoms attached to a carbon center, right? And then we're going to call that oxidation state one of 5 different names, 4 of which all start with an A, right? So the 5 oxidation states that we're going to talk about in this class will be alkane, alcohol, aldehyde, acid, and carbonate oxidation states, right? All of these are specific functional groups, but they're going to represent a broader oxidation state. Okay, so let me give you an example. Right, if we look at the alcohol oxidation state, right, the alcohol oxidation state includes all groups, or all carbon functional groups, where you have a bond to one electronegative atom. Right, so in this case, we're looking at that alcohol, right? We're saying that that alcohol has a bond to one electronegative atom. Right? What other functional groups would fall under this same oxidation state? No? Well, amine would fall under that same oxidation state, right? Because again, we have a carbon with one bond to a more electronegative atom, right? Ethers would fall under the same oxidation state. Alkyl chlorides or halides would fall under the same oxidation state. right? So we call it an alcohol because the alcohol kind of represents the electronegative bonding pattern in that oxidation state, right? But all of these functional groups and more, right, would fall under that umbrella of the alcohol oxidation state. All right, questions about that? Everybody sees what's going on here? Yeah. Okay. Aldehyde oxidation state represents functional groups with 2 bonds to more electronegative atoms. All right, so what other functional groups would fall under the aldehyde oxidation state? Yeah. Ketone, excellent. What else? Yeah.
Would the oxygen on the amide be the same?
So an amide is going to have 3 bonds to more electronegative atoms, right? So 2 to oxygen, 1 to nitrogen. So that's going to be different. What other functional groups do you know that have 2 bonds to a more electronegative atom? Yep. Carboxylic acid has 3 bonds, right? Joe?
About the alcohol hydrate, it's called, there's 2 alcohols.
Good. Hydrates.
Yeah.
Right, so those 2 bonds don't have to be a pi bond, right? Those 2 bonds can be 2 sigma bonds. So that should reveal a whole family of functional groups. Yep. Ketals, hemiketals, acetals, hemiacetals. Right, amines are going to be in that same group. Right, dihalo, so one of the solvents that we use in labs sometimes is dichloromethane. Right, so dihaloalkanes. Okay, so all of those fall under the aldehyde oxidation state because they all feature a carbon with 2 bonds to a more electronegative atom. Right, carboxylic acid, what other functional groups would fall under this umbrella here? Yeah. Esters, great. Any others? Just yell them out. Amides, great. Acid chlorides. Right, we can also have chloroform. You have things like orthoformates. Right, these are functional groups you haven't seen before. Doesn't matter, again, it doesn't really matter the bonding pattern, right? If it's a pi bond, if it's a sigma bond, it just matters the number of bonds to something more electronegative. Right, nitriles are part of this same acid group. Right, 3 or triple bond to a more electronegative atom. Right, and then the last one is carbonate. So these are things like carbonic acid, carbon dioxide, phosgene. Right, we won't do too much with these. We will look at them a little bit. Okay, questions about this? Okay, so again, right, the 5 oxidation states that we're going to be focusing on are, we name them according to a representative functional group in that oxidation state. 4 of the 5 start with A, so they should be really easy to remember, right? Alkane, alcohol, aldehyde, acid, and then carbonate is kind of the odd one out, right? People do oxidation state different ways, right? Some people use numbers, some people use numbers 1 through 5, other people use numbers 1 through 10. right? Because we're differentiating between bonds to carbon, bonds to hydrogen, bonds to more electronegative atoms. We're gonna try to keep things as simple as possible, right? So the idea is that anything towards the left side of this, right, is going to be on the reduced state, right? Anything towards the right side of this is going to be in the oxidized state, right? So a lot of you might have learned the mnemonic for oxidation and reduction oil rig. Anybody recognize this? So what does that mean? What does that stand for? Yeah.
Oxidation is loss, reduction is gain.
Okay, oxidation is loss and reduction is gain. And what is being lost and gained whenever we're oxidizing and reducing?
Charges.
Right.
The electrons.
The electrons, good, right? So we learned that when you lose electrons, right, you're being oxidized. When you gain electrons, you're being reduced, right? And so when we're thinking about losing electrons or gaining electrons, it's more about electron density around carbon. Okay, so with one electronegative atom, right, and when we go from one electronegative atom or one bond to an electronegative atom to two bonds to electronegative atoms, we're removing electron density from the central carbon, right? So as we increase the number of electronegative atoms around that carbon is losing electron density, right? So things are getting oxidized as we go from the alcohol, the aldehyde, to the acid, to the carbonate, because the more oxygens or more bonds to oxygen around a carbon, the less electron density that carbon has, right? Likewise, going the other direction, if we go from an acid to an aldehyde to an alcohol, right, we're typically replacing an oxygen, right, or an electronegative atom with a hydrogen or a carbon. So as we replace that electronegative element with a hydrogen or a carbon, we're going to be gaining more electron density around that central carbon, right? And so that's how we want to think about oxidation and reduction in organic chemistry. It's not, here are 2 electrons, right, and now this carbon has 10 electrons around it. It's how much electron density that central carbon has, right? As you go from an alkane to an alcohol, aldehyde, acid, carbonate, you're increasing the electronegative atoms around that carbon, decreasing the electron density, right? Losing electron density. So you're oxidizing, going the other direction, you're reducing. Okay. Questions? Okay, so the reactions that we're going to be focusing on in this chapter are all going to be reduction reactions. And we'll get to oxidation reactions probably next semester. Okay, so here's a scheme for the reaction that we're going to be looking a lot at today. So this is a reduction reaction where we're going from an aldehyde and reducing that aldehyde down to the primary alcohol. Right, so just like amines come in 3 different flavors, alcohols also come in 3 different flavors, right? So we have primary, secondary, and tertiary. With amines, primary and secondary and tertiary communicate the number of hydrogens a nitrogen has attached to it, right? With alcohols, it's the number of hydrogens on the carbon of the alcohol, right? So a primary alcohol is going to have 1 R group, right? Secondary alcohol will have 2 R groups and 1 hydrogen. And a tertiary alcohol will have 3 R groups and 0 hydrogens. right? So whenever we're reducing an aldehyde with sodium borohydride, right, we're producing a primary alcohol. Okay, so in the reaction we have sodium borohydride, and then we have isopropyl alcohol. And in this reaction, the isopropyl alcohol is going to be acting as the solvent. Right, and in particular, it's going to be a protic solvent, right? So it's a solvent that can give up protons. Right? Isopropyl alcohol is not the only solvent that we can use for this reaction. Alcohol solvents are typical, right? But we don't have to use isopropanol. Right? Isopropanol is just kind of a convenient solvent because it has a nice organic backbone on it. Right? And then the sodium borohydride is going to look like this. It's an inorganic salt, right? Ionic compound. The borohydride anion is a boron with 4 hydrogens around it. Negative charge, right? So it has an extra bonding partner. And then the sodium ion is counterbalancing that negative charge. Okay, the boron is tetrahedral. So I've tried to draw it to suggest that geometry. All right, let's go over the mechanism really quickly, see what's going on. Okay, so we have our aldehyde and we have our borohydride. Right. Whenever we draw the mechanism, we're going to draw the arrow through the boron-hydrogen bond. Okay, and that's being added to the carbonyl carbon. You can see it when we add that hydride, that H minus to the carbonyl, that takes us almost directly to the alcohol, right? The only thing that we need to do is protonate the product that forms, right? We can do that in this case with the solvent, isopropanol. Right, and that gets us our product. Okay, so even though we have our product, I do want to go over what the fate of this borane is, right? So we use the borohydride, we create something called BH3, which is called borane. Right, and that borane is going to react with an alkoxide. That alkoxide could be the alkoxide that we formed here, all right? But it can also be the alcohol that gets deprotonated in the reaction. right? And what that does is it reforms a hydride donor, right? So you can see our hydride donor in the first step is BH4, right? Here it's BH3 with an alcohol attached, right? And this is still going to be able to deliver a hydride, H minus. Right, so let's focus on the first step of this mechanism. All right, we're going to talk about how these molecules are interacting or what orbitals are overlapping, and take a little closer look at sodium borohydride as a reagent. Right, so when we look at the first step of this mechanism, what is the HOMO and the LUMO, according to the way that we drew our arrows anyway?
Would the HOMO be the hydrogen boron sigma?
Excellent. Right, so the HOMO, right, the arrow shows the mechanism shows the arrow going through the boron hydrogen sigma bond, right? And so the highest occupied molecular orbital is going to be the boron hydrogen sigma bonding orbital. Right, so it's the sigma bond where the electrons are coming from, or that's doing the overlap with the LUMO. Right, what's the LUMO in this case? That should be easy.
Is it the anti-bonding pi orbital?
Good, so the carbon oxygen pi star pi anti-bonding orbital. Right, so again, it's the boron hydrogen sigma bond that's overlapping with the pi star orbital on a carbon. Right? If we think about that boron hydrogen sigma bond, or if we think about the structure of borohydride, we put a negative charge, formal negative charge on boron. Right? But we have to think, to understand the reactivity of that reagent, we have to think more about the polarity of the boron hydrogen bond. Which way are those going to be polarized, boron hydrogen bond?
They all point towards the boron.
No. Good guess, 50-50 guess, yeah.
The other way.
The other way, good. Right, so hydrogen is actually slightly more electronegative than boron, right? Based upon what you would see on a periodic table, you might guess boron is more electronegative just because hydrogen's in the upper left corner, right? But that's kind of in a weird place if you consider its electronegativity value, right? So in this case, all these bonds are polarized towards hydrogen, which gives the hydrogens a partial negative charge and the boron a partial positive charge. Right, so we put the formal negative charge on boron to show that there's more electron density on this molecule, but that electron density is really concentrated on the hydrogen part, or on the outside of the molecule. And so whenever this molecule interacts, and the boron hydrogen sigma bond overlaps with the pi star orbital, the electrons, because hydrogen is more electronegative, the electrons stay with hydrogen, right? And then they get delivered to the carbonyl carbon. Right, questions about this? Yeah, Joe.
Would you consider the hydrogens in this case to be nucleophilic?
I would, yes. Yeah, excellent. Yeah. Right, and I would start to distinguish this from being basic, right? So these hydrogens are great nucleophiles. They can add to carbon, add to carbonyls. They're not very good bases, right? We can show a mechanism, and they are weakly basic, right? But they're not very good at plucking protons. Really good at adding to carbon, not good at plucking protons. Other questions? Bless you. All right, see if you can figure out really quickly the product of this reaction. Once you get the product, see if you can name it. Give it an IUPAC name. Okay, anybody come up with a product? We don't name the product yet? You-
Hold on, I didn't name this.
Okay.
I have 1,3-cyclohexanol.
Almost, yeah. So 1,3-cyclohexane diol.
Damn it. God, sorry.
That's all right. Okay. All right, so what we're going to be doing is delivering a hydride to each carbonyl. I'm not going to drop the mechanism. We don't have enough time. Hopefully everybody can understand what's going on here, right? So we're reducing one ketone, protonating that ketone, right? Reducing the second ketone, protonating that second ketone. Yeah.
So essentially this would happen in 4 steps?
This would happen mechanistically, yeah, we could draw four steps, right? When we draw the mechanism, right, we have to draw the reduction of each ketone separately. Right? Because if we draw them at the same time, we're saying that whenever reduction occurs, reduction on both ketones is always going to happen at the same time. Right? And that's not the case. Those are two independent reductions. So we would show the complete reduction of one, protonation of that same one, right? And then move on to the other functional group. Any questions about that? Okay. So if we take an aldehyde and reduce it with sodium borohydride, we get to a primary alcohol. We take a ketone and reduce it with sodium borohydride. We create a secondary alcohol. right? If we try to move to an ester and treat an ester with sodium borohydride, what we're going to be doing is basically sitting there and staring at the reaction and not seeing any product form. Right, so aldehydes can be reduced with sodium borohydride, ketones can be reduced with sodium borohydride, but esters cannot be reduced with sodium borohydride. Why would that be? So sodium borohydride can react with aldehydes, right? Can react with ketones, right? This reaction with esters is too slow, right? It can react, just the rate of the reaction is too slow to make this a useful reaction.
Because, like, in the electronegative, we saw that ester is really less electrophilic.
Good, so we talked about the trends in electrophilicity of the carbonyl compounds, right? And we saw that esters are going to be less electrophilic, less reactive, right, than aldehydes and ketones. Okay, so this is a good enough nucleophile to add to this electrophile, right? It's a good enough nucleophile to add to a ketone electrophile. It's not a strong enough nucleophile to add to an ester, right? This ester has too much electron flow going through the carbonyl carbon, right? So it doesn't want an external nucleophile as much, and sodium borohydride is not a good enough nucleophile. Right, questions about this? All right, we'll return to this on Wednesday. We'll talk about a similar reducing agent and maybe get into some gradient chemistry.